All right, so we're going to go ahead and look at applying the concepts that we talked about in the first video. So this is for chapter 7, work and kinetic energy. Okay, and I'm sorry if there's a little bit of background noise. I am recording this from the school, so it's slightly louder than my apartment. So we have an intern who's pushing a patient on a gurney, and it produces an acceleration, which is given here. And I will use the pointer. So we want to know how much work this intern does over a particular distance, and we're assuming the gurney moves without friction. So we can also assume here that the force that this intern is using to push the patient, well, it's probably constant. So we're just going to use the simple formula work equals force multiplied by the distance or the displacement. Well, this should be fairly easy. I don't even think we need to draw a picture here, though you might. So we have force. It didn't explicitly give us force, but we do know that force is equal to mass multiplied by acceleration. Well, we know the mass here is 18 grams and 87 grams. So we're going to actually have to add those together because the intern is pushing the patient who is on the gurney. So the intern is pushing the weight of both. So this would be 87 kilograms plus 18 kilograms. Oh, I forgot my unit there. I'm so sorry. And we're going to multiply it by the acceleration, which is 0.55 meters per second squared. That's equal to our force. When we solve for that, you should find that the force is equal to 105. Oh, I am so sorry. I don't even know where that came from. It is not 105. It is 58 newtons. So we can take this information and plug it in here. So we know that work is equal to 58 newtons multiplied by the distance, which is 1.9 meters. So work is going to equal 110 joules. And I used two significant figures here. We see 2 in each of these values, so we need to use 2 as well. That is part A. Now for part B, I want y'all to pause the video and try it yourself. Okay, so for part B, that was part A. I'll just draw a little line here. Here's part B. How far must the intern push the gurney to do 140 joules of work? Well, now that we have calculated the force, this will be pretty easy. We're just going to plug everything in, which is 140 joules equals the force, which is 58 newtons multiplied by the distance. And you should find that the distance is 2.4 meters. So that's parts A and B. Next, okay, we want to load a box into a truck. And here we're not going to do much math. We're just going to think about this conceptually. So we can either lift this box straight up onto the truck, or we can carry it up the truck to the top. So we want to know if the work done here in the first problem is greater than, equal to, or less than the work done here in the second problem. So let's think about this. And I will do a little math just to help you understand what's happening. So in this first one, in this picture here, we're going straight up. So we can say our work here for number 1, I'll say work 1, is equal to the force multiplied by that distance. And in our case, our force is going to be equal to the weight, which is mg, and our distance would be h. Okay. Over here, for the second one, well, this one's going to be slightly more complicated. Because we have an x and a y direction, since this is diagonal. However, this box is not moving vertically. It is moving up the ramp. So we're going to call this the x direction. So we're going to say this box is only moving in the x direction. So we have force times distance. And that is equal to, now this time, since we're talking about the x direction, and the force from this box will be equal to the weight, it's going to be mg sine theta, and the distance it travels is L. Well, if we want to know what sine theta is, because obviously we can't really relate these right now, we can use trigonometry or geometry. We can use SOHCAHTOA to see that the sine of theta is just the opposite over the hypotenuse. And in our case, that's equal to h over L. So let's replace that. FD equals mg h over L multiplied by L. We can cancel out the L's, and that leaves us with mgh. So work 1 and work 2 are going to be equal. Number 3, we have a car that is coasting down a hill. Okay, it's coasting, and we know when something is coasting, the force is likely variable. So we're not going to keep a consistent speed. We're going to speed up the further we get down the hill. Since we're working with a variable force, we can't just use our simple work equals force times distance. We will have to use the other formula, the one for variable work, which is that work equals the force times the distance times the cosine of theta. Okay, so we know that. This car is acted on by multiple forces. We have the normal force that's exerted by the road, we have a force that's due to air resistance, and we have the force of gravity. So we want to find the total work that's done on the car as it travels that distance. I can quickly sketch this. So here is our road. I'm going to let this rectangle with some circles be our car. Remember, the normal force is perpendicular to the surface. So there's our normal. And the weight of this car will go straight down. That'll be mg. Let's use some other color. Okay, I'm going to set my coordinate system like this because I want the x direction to be equal with my surface. So here's my x direction. And there's my y direction. Okay. Oh, and then I left out a force, and I apologize for that. We need air because it says we have a force due to air resistance. So if the air is this way, we'll say here's our force due to air. So we need to actually add up all of these so we can find the total work done. We can't just take one of these and ignore the rest. So let's do the work from the normal force first. All right, I'm going to call that work from normal force, Wn, and I'm going to isolate it here in my system. So I see that if I were to redraw this, the normal force right here goes only in the y direction. And it is at a 90-degree angle to this surface. Okay, so here is 90 degrees. If you recall from the concepts video, when we have our force and our distance perpendicular to each other, the work is simply equal to 0. We can also solve that if you're not sure what it looks like. So that would be FD. But we are going to have to replace that, and it would be in cosine theta because it's going in the y direction multiplied by d. If you put 90 degrees in here, You will get 0, so we know the work from the normal force is equal to 0. Second, we want the work from the weight, which I will actually write out. And here, weight has both an x and a y component. So we will need to do a little bit of extra stuff here. Okay. Since it has both components, we are going to use, we can't just use force times distance. We're going to use force times distance times cosine theta. Now, what is this angle? Well, if I draw the surface up here, like this, all the way across, we know that this is our angle, and we're looking at weight here. We're focusing on weight. To figure out what we would end up placing here for theta, we would say theta is equal to 90 minus some value. We're not sure what that is. Okay. So we're going to use that and plug it in. So we're going to plug it in here. And we have FD cosine 90 minus x. And you might have forgotten this, but we can actually use a trig substitution here. The cosine of 90 minus x is just equal to the sine of theta. So when we do that, we find FD sine theta, and that's going to be the work associated with the weight. And now we need to do our final portion of the work, and that is that the work of air. And I will separate this portion out too. Okay, so this is the work from air. I'm running out of space here. The work from air is moving only in the x direction. So, and we see that it's going in the negative x direction. That might be important. So we're going to say that, I've already written it here, the work from air is equal to the force. Again, this is not variable, or this is not constant, so it's going to be times the cosine of theta times distance. We can make a couple of substitutions here. Number one, we know our forces are due to the weight of that vehicle, so mg. Cosine theta, it is moving only in the x direction, so we know that's 180, and then distance. And when we calculate this, we'll find that the work associated with air resistance is negative FD. So when we take these values and we add them up, so we have this, we have the work from weight, and we have the work from our normal force. When we add all of those up, we will find that our total work, so work total, and I apologize for the messiness of this, is mg, and again, I'm just replacing force with mg because our force is due to our weight. I'm going to rearrange it, mgd sine theta minus, and this is the force from air times the distance. So here would be the final answer. And if part of that wasn't clear, please just let me know and I would be happy to answer your questions. Okay, I'm erasing this. For the next one, we have a motorcycle that is cruising. Okay, and we want to know the work done if it's going to increase its speed. So in the previous video, we talked about relating speed or velocity to work. And we used this equation. The total work equals 1/2 mv final squared minus 1/2 mv initial squared. Now, this one, you'll probably like this problem. This one is nice and easy. We can just plug in all our information. We have our mass here. We have our initial speed here because it says it's cruising at 14 meters per second. So here's VI. And it's increasing its speed to this. So once we make those substitutions, you should find that the total work is equal to 18,000 joules. And that's all you do for this problem. Nice and short. Moving right along, we have a box of books that's going to be lifted vertically. So we're going to be moving the box a distance of 1.60 meters. So we're moving it, in this direction, 1.60 meters. And there's a constant applied force upward of 52.7 newtons. So here's my box. I'm going to draw the force going up, 52.7 newtons. And as with anything that has mass, we know there's going to be an opposite force. That's mass times gravity. Since it's moving upward, we can assume that this upward force is larger. Okay, so I want y'all to take a moment and see if you can work this one out yourselves, and then press play when you're ready. All right, since we're working with multiple forces, we know that work is equal to force times distance times the cosine of theta. And let's go ahead and look at part A. And I hope y'all were able to get this right. Okay, so the work done by the applied force is constant. So that makes this first part pretty easy. Work is just equal to force times distance. Therefore, and we can technically use the other formula. We can technically say force times distance times cosine theta, but because this theta is 0, it will disappear anyway. So we just say that it is force times distance because it would just be 1. And when you plug your information in, 52.7 newtons multiplied by 1.60 meters, you should have found that the work from the applied force is equal to 84.3 joules. So that's part A. Part B, the work done by gravity. All right, this one is slightly more complicated, but it's really not too bad. So in this case, we would have gravity and we have a force going this way. So we are going to say force times distance times cosine theta. Cosine theta, this is in the y direction. And that's equal to, remember, this force is just equal to our weight. So mg is mg times the distance times the cosine of theta. In our case here, theta is 180 degrees because our angle here, it would be 180. The angle between the applied force and gravity. And so when you plug all your information in here, mass, gravity, and distance, and then the 180, you should have found that the work from gravity equals negative 64.4 joules. And this matches with what we talked about in the concept video, where when we talked about the different angles for the force, that it will be either positive, negative, or 0. Work will be positive, negative, or 0. Here, since we have an angle of 180, we see that the work is negative. And finally, part C, we want to know the total. The final speed of the box, but in order to do that, we need the total work. So we need to add together the 84.3 and the negative 64.4 to find our total work first, which would be 19.9 joules. And we're using that formula, W total, I'm going to abbreviate that as T, is 1/2 mv final squared minus 1/2 mv initial squared. Plug all of the appropriate information in, with your total work being 19.9 joules, and you should have found that your final velocity is 3.12 meters per second. And that will be your final answer here. Okay. Again, please let me know if you have questions about any of these. Sometimes it can be difficult to explain certain portions of this through video. For this next problem, we're going to look at an AFM cantilever. And I'm going to be honest, I've never even seen this. So it is perfectly fine if you don't know what this is. You should still be able to work the problem, and you'll likely find it's pretty easy because it says, what is the force constant when we're treating this as an ideal spring? Okay, so we have our nanometers here, and that's our distance. And we have our joules, so that's our work. We want to know the force constant, and it says it's being treated like an ideal spring. And we know that work for an ideal spring is 1/2 kx squared. Again, I hope y'all wrote all those formulas down and that you actually have them near you so that this process is a little bit easier in determining where I'm getting these formulas from. We want to rearrange this so that we're solving for k, which is the constant. So k equals 2w over x squared. And then we're going to plug in our information. But before we plug that in, notice here that we have nanometers. We need to convert that to meters. And when you do, you should find that 0.01 nanometers is equal to 1 times 10 to the negative 10 meters. So you're going to plug in all your information. 2 times 1.2 times 10 to the negative 20th joules divided by 1 times 10 to the negative 10 meters squared. And that equals 2.4 newtons per meter. Okay. So that one was pretty simple, even though we don't know what a cantilever is. Or maybe you do. Okay, for the next one, we are just moving right along here. Oh, my goodness. I just realized that I forgot to explain the second part of this, and I apologize for that. I did not do part B. Wow, where is my mind? Okay, so we found part A, which was the spring constant. Let me just write that back down. K equals 2.4 newtons per meter. I'm glad I caught myself. I would have had to make a third video. Okay, so part B, how much work is required to increase the deflection of that cantilever from 0.10 nanometers to 0.20 nanometers. Okay, so we want to know the work required to increase from 0.10 to 0.20 nanometers. So we're going to have to find work first for both of them. Well, really only for one. It gave us work here for the 0.10 nanometers. So we already know this. So we need to calculate it for 0.20 nanometers. But this will be very straightforward because we already found our constant. So W equals 1/2 kx squared, which equals 1/2 2.4 newtons per meter multiplied by, and when you convert 0.20 nanometers, it is 2 times 10 to the negative 10 meters squared. You'll find that the work is equal to 4.8 times 10 to the negative 20 joules. We want to know how much it increased, so we just need to find that difference. So we'll say 4.8 times 10 to the negative 20 joules, because that's the 0.20 nanometer value for work, minus the one for 0.10 nanometers, which is 1.2 times 10 to the negative 20 joules. And we'll see that our difference is 3.6 times 10 to the negative 20 joules. So that would be our final answer to part B, which I tried to skip and I apologize for. Okay, so there's part B. And now we are moving right along. Here we see that we have a slow-moving truck that you're trying to pass in a very fancy car. We have that car's mass right here. And we see that we want to accelerate from 13.4 meters per second. So we have an initial velocity. We're going here to 17.9 meters per second, which would be our final velocity. Ooh, you can barely tell that that is an F. I am so sorry. Just erase that. V final. Okay, and then here we have our value for time. We want to know the power required. So let's grab the power formula, which is power equals work over time. Okay, to find power, we need work, but we don't have work. However, we do have the initial and final velocities, and we have the mass. So we can calculate work, because work equals 1/2 mass times velocity, the final velocity squared, minus 1/2 mass times the initial velocity squared. When you plug in all of this information, you should find that that work is equal to 9.16 times 10 to the 4th joules. We can take this value and plug it in. So P equals 9.16 times 10 to the 4th joules divided by 3.00 seconds. And it equals 3.05 times 10 to the 4th watts. And you'll see that the sig figs are consistent. We have 3 here, 3 there. So I had 3 in my answer. If I want to convert this into horsepower, and I provided that information to y'all in the previous video, it would be 40.9 horsepower. And if you have forgotten that information, I'll put it down below just so you know. 745.7 watts is equal to 1 horsepower. Okay, so there is our final answer for power. You could leave it in watts or horsepower. It doesn't matter to me. Obviously, if it's a quiz or a test, you would want to look at the answer choices. And here we are at the final question. We have a car that is on a slope of 5.25 degrees. We see that we are given 4.10 times 10 to the 4th watts, which is 55 horsepower. So we are told the power. Here's our value for power. And we want to know the maximum speed of the car. If you recall, towards the end of the concept video, we talked about how power, which is W over T, we can rewrite that. We know that work is also equal to force times distance, so we can replace it and say force times distance divided by time, and then we can separate this. And because distance over time is equal to velocity, we can just say power is equal to force times velocity. We have the force and we have our power. So all we need now is the velocity. Let's plug it all in. I'm going to rearrange this first to find velocity is equal to power divided by force. And let's plug in what we know, which is 4.10 times 10 to the fourth watts, or horsepower, it doesn't matter which one you choose, divided by 1450 newtons. So we did not even need this value for mass or this angle theta. It was just there to throw us off. We do this math and we can find that the velocity is equal to 28.3 meters per second. So there's our final answer for the maximum speed of the car. I hope you were able to follow along. Again, if you have any questions, I would be happy to answer them. Reach out to me through Canvas, and we can talk about it through Canvas, or we can set up a meeting to discuss this more. Thank y'all for watching.